So in this video, I'd like to go over homework number 3. And homework number 3 isn't, you don't need to turn that in, but I still highly recommend going through it. So anyway, number 1 says elementary gas phase, you have an elementary gas phase reaction, A to B plus C, is taking place in a PFR, a plug flow reactor. The molar flow rate of pure A is 5 moles per minute at 12 atmosphere pressure and 177 degrees Celsius. The rate constant at the given temperature is 0.2 per minute. So then you want to find the PFR volume for 85% conversion of A. So I'll just start writing some of that down. So you have a reaction that looks like this. A to B plus C. You know it's elementary. It's gas phase. It's in a PFR. You know that the molar flow rate is of pure A is 5 moles per minute, and this is at pressure is 12 atmospheres, and the temperature is 177 degrees C. And then you know that it gives you the rate constant at this particular temperature. So if you remember, the rate constants are dependent or can be dependent on temperature. So that's why it's giving it to you for a specific temperature. So K is equal to 0.2 and then you want to find find volume of the PFR, and for XA is equal to 85% conversion. So then we also want to make some assumptions. First of all, I'm going to assume that for these calculations anyway, that it's isothermal and that there's no pressure drops. So no pressure drop, isothermal. So the first thing you want to do is, or at least the way I usually approach these problems is I just go through steps. So first I write down the design equation, and then I write down the rate law, and then I find the concentrations, and then you can combine everything and solve it. So first of all, the design equation we know it's a PFR, so we want the PFR design equation, and that is FA naught dx dV equals minus RA, or the rate. And then since we're assuming that there's no pressure drop, we can rearrange the equation to the integral form. So B is equal to FA naught 0 to x dx over minus RA. So then we need in order to solve this, we need the rate law. So that's next. This is the design equation. And then we need the rate law. So for the rate law, it tells us this is elementary. So we know that this will be minus RA, and we're getting that from that equation, so we know that it's C. Well, we know that it's since it's elementary, we know that it's K Ca, so the rate constant multiplied by the concentration of A. And so then we need an equation to find the concentration of A. So and this is what you would get from the tables in chapter 3, and I think they're also in chapter 4 and chapter 5. So since this is gas phase and we need to use the concentration equations for gas phase, and it's a good idea to understand where these equations came from, but for this I'm just going to copy it from the table. So we know that Ca is equal to Fa over B, and that is equal to Fa naught 1 minus x over B naught 1 plus epsilon x, and then we know that this is Ca naught, so this equals Ca naught multiplied by 1 minus x divided by 1 plus epsilon x. So then we can just combine everything. So we put this into here, and this into here, and then we're going to solve that equation. So doing that, you get B is equal to Fa naught 0 to x dx over K Ca naught. So I'm plugging this in. 1 minus x over 1 plus epsilon x. That's still on the board. So then this is equal to Fa naught 0 to x 1 plus epsilon x dx over K Ca naught 1 minus x, and then pulling out these constants, we can rewrite this as Fa naught K Ca naught, and we can pull K out because we're assuming it's isothermal. 0 to x 1 plus epsilon x dx over 1 minus x. Alright, so then you can look up this integral in there's a table of them in the back of this textbook, Elements of Chemical Reaction Engineering, or you can also solve it on your calculator or however you want to solve these. So this ends up equaling Fa naught K Ca naught 1 plus epsilon natural log 1 over 1 minus x minus epsilon x. So the volume equals that. So then this is the equation we want to solve. So I'm going to erase some stuff, and then I can show you how to calculate the parameters that you need for that equation. So I'll just rewrite the equation real quick so it's easier to read. So your volume is equal to Fa naught K Ca naught 1 plus epsilon natural log 1 over 1 minus x minus epsilon x. So we know this because it was given. We know we can calculate Ca naught from the gas law. We know this because it was given. So we need to calculate this, epsilon. We know x. So we need to calculate Ca naught and epsilon. So first of all, we calculate Ca naught from the gas law. So Ca naught is equal to y a naught p naught over r t naught. And then we know that ya naught is 1 because it told us in the problem statement that let's say that. It says the molar flow rate of pure A, so there's nothing else in the mixture. So this is, so I'll just write, oh yeah, so I'll just write 1. So ya naught is equal to 1. And then we know P naught because it gives it to us, so 12 atmospheres over. And then we, for the, for R, you want to pick, so that's a gas constant, you want to pick that, you want to make sure you pick the right one because there are a whole bunch of them and they just have different, they're all the same but they just have different units. And so what I did was, there's a, Wikipedia has a really good page with all the constants or with all the different units. So I actually printed that out and put it in my notes because it makes it easier to just look at the units that you already have and then just use the right constants. So the one I'm using here is 0.082 dm cubed atmosphere over mole K. And then the only thing is the temperature for this is in Kelvin, but our temperature is in Celsius, so you just need to remember to convert your temperature to Kelvin. So that is 450.15 Kelvin. So then if you cancel things out, you can see that you have mole per dm cubed, so you have an amount per volume, which is a concentration. So then you know that this is correct. So this is equal to 0.325 moles dm cubed. And then I'm going to erase some more stuff. The second thing we need to calculate is this epsilon. So we know that epsilon is equal to ya naught delta. And so we've already determined that ya naught is equal to 1. So we need to calculate delta. So delta is equal to, actually that's not on the board. So delta is equal to, in this case, C over A plus B over A minus 1. And if you don't understand where this came from, you need to review that because this is pretty important. So this is equal to, and so C over A, we have 1 over 1 plus B over A 1 over 1 minus 1, so that equals 2 minus 1, which is 1. And then, so then we plug that in. Epsilon is equal to 1 multiplied by 1 equals 1. So then you should have everything you need. So plugging everything into here, we have V is equal to FA naught, which is 5 moles per minute, over K, which is 0.2 per minute, Ca naught, which is 0.325 moles per dm cubed. I don't think you're going to be able to see the rest of this when I write it, so I'll just write it down here. So then we know that epsilon is 1, so 1 plus 1, natural log 1 over 1 minus x was 0.85 minus 1 times 0.85. So then you just need to plug all that into your calculator and solve it, and you should get 226 dm cubed. Number 2 says you have a reaction with no volume change is carried out in a CSTR A to B. So I'll start writing that down. So you have A to B CSTR, no volume change. The entering concentration is 2.5 moles per liter. So you have FA naught equals 2.5 moles. Actually, this is the entering concentration. So, and then you observe a conversion of x equals 0.5 XA. And you wanted to achieve a higher conversion than 50%, so you ended up installing a PFR that you expected to get 63%. So you installed PFR with the expected XA equals 0.63, but you actually got 67, so actual XA equals 0.67. So why would this happen? That's the entire point of this problem. You want to figure out why you were expecting this conversion, but you actually got that one. So first of all, let's look at the PFR design equation. So V equals FA naught 0 to x dx over minus RA. So it's all, if we're not changing the entering concentration or the entering flow rates or anything like that, it seems like this change would have to do with the rate law, looking at the equation. So let's just try some different rate laws and see what we get. So first of all, if we write down the rate laws, first of all, let's assume that it's first order, and that it's elementary. So then this would be K CA. And then doing the stoichiometry, we know that CA is equal to CA naught 1 minus x. And it's this, we're using this equation because there's no volume change. And so then if we combine this, we get V is equal to FA naught 0 to x dx over k CA naught 1 minus x. And so then we can pull these out. So that is equal to FA naught k CA naught 0 to x dx over 1 minus x. So then solving this, we get, and once again you can just look this up in the appendix in your book or solve it, just solve it with your calculator, however you solve these. So that is equal to FA naught over K CA naught. So multiplied by the natural log of 1 over 1 minus x. And then we also know that FA naught is equal to CA naught V naught. So I'm just going to go ahead and replace that. So that cancels out. So we're left, we're left with V is equal to V naught over K multiplied by the natural log of 1 over 1 minus x. And then we can rearrange this so we can multiply the k over and divide V naught over, so we get V over V naught multiplied by k equals the natural log 1 over 1 minus x. And then we know that this is tau, which is space-time. And so to solve this equation, we're actually missing some information. We don't know what this is, the tau k, but we know enough information from that CSTR that we can calculate it. So we'll do that real quick. Get tau k from CSTR. So writing down the CSTR design equation, we have V is equal to FA naught x over the rate. And so we already know the rate because we're using the same rate as before, and that was the minus RA is equal to K CA, which was K CA naught 1 minus x. So we just put that into here. And then we also know that FA naught is CA naught V naught, so V is equal to CA naught V naught x over K CA naught 1 minus x. CA naught cancels out, so then we can divide over V naught, multiply over K, so we have V over V naught K, which is equal to tau K is equal to x over 1 minus x. And then we know what x is for the PFR. It was 0.5, so we can plug that in. 0.5 over 1 minus 0.5. So then solving that, we get that tau k is equal to 1. So then going back to the PFR, we can plug in 1 for this, so going back to this equation, we have 1 is equal to the natural log of 1 over 1 minus x. And so in this case we're solving for x, and we should be able to do that. So solving that, we get that x is 0.63. So then we can see that this is the calculation that the engineer did originally, because this is what they expected to get, but they actually got 0.67. So then based on that we can say, okay, well, maybe we assumed it was first order, so maybe it wasn't first order, maybe it's second order. So let's try a second order rate real quick. Try second order. So then writing a second order rate law, we get minus RA is equal to K CA squared. So I'm just going to erase some things real quick so I have room. All right, so we're trying a second order rate law. So our rate law looks like this. Minus RA is equal to K CA squared. And then can go ahead and do the stoichiometry real quick. So in this case it would just be K CA naught squared 1 minus x squared. And then we already know that based on how we solved this problem in the previous step, we needed to get information from the CSTR in order to solve for the PFR. So I'm going to go through the CSTR again with the information we know, and what we're looking for is this tau k again. Well, the tau k CA naught. So the CSTR design equation once again is V FA naught x over minus RA. And then just plugging stuff in again, just remember that the FA naught is equal to CA naught V naught, so we can put that in CA naught V naught multiplied by x over, and then we put this in, so K CA naught squared 1 minus x squared, that cancels out. And then we can rearrange this so we can get V over V naught times K CA naught, which is equal to tau K CA naught is equal to x over 1 minus x squared. And then if we plug in the 0.5 for x again, this ends up being equal to 2. So then we can go ahead and finish the PFR. So PFR design equation is B FA naught 0 to x dx over minus RA. And one thing I've been doing as I solve these problems is, so I'm basically solving the same equation over and over and over, but I always, and so like in this case, I probably could have, instead of writing this down, I probably could have just jumped straight to this one or somewhere else along the line. But I always write down the beginning equation and start there, because I feel like it's easier to get confused if you try and jump into some of these equations further down the line, because you might be making some assumption you can't make or something else. So I feel like it's easiest to just always start from the design equation. So like for instance this one, I could probably, well, if I still had my stuff written down, I could probably just jump straight to There's one of them. Like, practically solving it, but I just feel like it's better to start here and then work through it again, especially when you're just starting to learn this stuff. So anyway, for the PFR, so once again we can plug in FA naught and the rate. So then this is equal to CA naught V naught 0 to x dx over K CA naught squared 1 minus x squared, and then that cancels out again. So then this is equal to, well, and then this is V. So I'm going to divide over the V naught and the multiply over the K CA naught. So then you can see that we already know what this is equal to because we got it from the CSTR. So then this is equal to 0 to x dx over 1 minus x squared and then if I solve that, so then I get tau K CA naught is equal to x over 1 minus x, and we know that that's equal to 2. So then you can solve for x and you get the x is equal to 0.67. So then you can see that since when they ran this PFR, they measured a conversion rate of 67%. So then you can see that based on experiments, this reaction must actually be second order.